Hola.
Is this better? Better. Had to check my microphone. Yep, it's on. All right, guys. Thank you for your understanding. Thank you for being with me in class today. I think I'm not sharing my screen. Somehow I stopped that. There we go. Make me go away because I don't want to see me. Just a quick update. My wife is doing awesome. She had a dance party in the ICU today, and it got her kicked out for being too rowdy. So they're moving her upstairs. She's breathing fine. Her heart is stabilized, thankfully. She had a pulse rate of 20 when she was admitted on Friday, and they got it stabilized, and I'm pretty stoked about it. It'll be a couple more days before she can get out, and so it's going to be a couple more days before I'm willing to leave the general area. But here we go. We got this. Let's talk about chapter 5. Excuse me. Chapter 5. Now, some of you may be thinking, what about 4.6? I am going to make section 4.6 extra credit. Let's just do that now. Nope, I can't do that now because you all are watching the screen. Okay, I'm going to make 4.6 extra credit. Numerical integration is important to know and understand that it's not just rectangles. We could use trapezoids as well, and trapezoids sometimes fit our curves better. There's one problem that one of our students that kind of works ahead a little bit had difficulty on, so I'm going to write that up for everybody on 4.6. But otherwise, we have 8 days of lecture as far as I'm concerned this week and next week. And then we're going to review for the rest of the time. We're just going to, and we might even look at problems you might see in future semesters. We're going to have some time to really look at what calculus is going to do for you. So we're going to start chapter 5. And here we're going to get into log functions and exponential functions and inverse trigonometric functions and all the differentiation and integration that goes with them. So We saw limits and derivatives. We saw uses of derivatives in chapter 4. We saw ways to find antiderivatives or integrals. And now we expand what we know. Okay, so first of all, the natural log of x, right? We know that's the inverse function of the natural exponential function, but it actually has a definition. It's an indefinite integral. Well, it's kind of it's a definite integral with an upper limit that is a variable. So this is how the natural log is actually defined, and it's going to help us in terms of derivatives and antiderivatives. Remember, we're going to be using natural log, so base of e for most of it. Log function's not going to be much different, but once we get the natural log down, the regular log functions will be fine. Domain of a lateral log function. Let's draw something here. Where's black when you want it? Okay, so the natural log function, I guess we're sticking with purple. Right, looks like this. The domain is 0 to infinity. The range is negative infinity to positive infinity. It's continuous, it's increasing, it's 1 to 1, so it has an inverse. The graph is concave down. We know all sorts of things about the natural log graph. And we also know a lot of things about logarithms in general. We know the product property of logarithms. We know the power product, or excuse me, power property of logarithms, and we know the quotient rule for logarithms. Quotient property is probably what it's called. All right, so this part is just algebra, which we know, of course, means it's the hard part, all right, but it's just algebra. This is new, definitely very new definition, and we almost never really use this again. Like we come and we define it. It's like that absolute value function is defined as a piecewise function. We just call it absolute value. The natural log of x is defined as the antiderivative from 1 to x of 1 over t dt, as long as x is greater than 0. And while this is the definition, we just call it natural log of x. So we're not going to be all pompousy and write this all the time. Now, the important calculus stuff here is the derivative. The derivative, when x is your variable, of the natural log of u is 1 over u times du dx. I use this representation the most. This is the derivative of the inside divided by original inside. That's it. All right. And the same is true even if you have an absolute value. It turns out that the domain of the log is non-negative anyway, so the absolute value doesn't really change anything. So the derivative of the natural log function is going to be derivative of the inside divided by the original inside. Now, your first 5 problems in the homework, they're just algebra. Literally just algebra. What's the graph of the negative natural log of x over 3? You throw it on Desmos or your calculator, sketch the graph of 3 natural log of x. Let's just go ahead and do one of these and make it easy on ourselves. All right, what is the domain? It's from 0 to infinity, always. Now, inside is just an x. We know exactly what that domain is. Let's not make this harder than it needs to be. You already passed pre-calculus. I'm gonna be so bummed if I get that one wrong. Yay, okay. Evaluate, use substitutions. Here's decimal approximations. Remember, only approximate, only round as a last step. Use properties of logarithms to expand the function. So log properties. Write the expression as a single quantity. So use the expanded ones and write them this way. You've seen 1 through 5 before. What we care about are problems 6 through 13. So let's do some work on these. All right, I am going to check real quick. I'm not going to check in with anybody in particular, but Can you all hear me all right? We doing okay? I just need one thumbs up, one yep, one I don't care, anything. Awesome. Thank you very much. Here we go. But for reals, I want black. Okay. So find the limit. The natural log of x minus 7. What we know is this shifts the graph 7 to the right. So if we graph the natural log and then shift it 7 to the right, it'll look like this. But we want to know what's going on as x approaches 7 from the right. So as I'm coming in here, what happens to my y values? Well, my y values round your answer to 4 decimal places. I'm thinking this is very negative infinity. There's not much of a decimal place I could put with that. But notice, even though it says round to 4 decimal places, it brings up the box because it knows that you're going to not actually have decimals. All right, just reminding you that as we move the function, all right, the limit adjusts and moves as well. So don't get all, when it comes to limits. Limits, that's all good. You could do that. I got a whole bunch of dots on my page like it's the measles or something. But we have vaccinations for the measles, so people don't catch it anymore. Just saying, super happy my wife is vaccinated. Okay. Find the derivative of the function. This is the natural log of u if u is 8x over x plus 9, right? This is our inside. Throw a dot over there. So we know the derivative is the derivative of u over u. So let's find what this derivative is. In order to find this derivative, we use the quotient rule, which tells me I probably didn't leave enough room here, but it's low d high minus high d low all over low squared. And squared, don't forget squared. And when we multiply this out, see how we'll get an 8x here and a minus 8x, they cancel out. So it looks like u prime, don't forget this is the derivative, is 72 divided by x plus 9 all squared. So our derivative is 72 over x plus 9 squared divided by 8x over x plus 9. But we know if we are dividing by a fraction, we can multiply by the reciprocal. And when we do so, where our x minus 9s are going to cancel out. One of them cancels this one. 8 goes into 72 9 times. So we will have 9 over x times x plus 9. Let's see if it works. 9 divided by x times x plus 9. Fantastic. So a big question is, can you write it just like this? Possibly. But you know what we do, right? We learn to take a derivative so we can use it. So this is absolutely going to be the preferred format for the answer. You can multiply it out, call it x squared plus 9x if you want to. You can leave it in factored form also. But this ginormous double fraction, complex fraction is not going to be the best. All right, so hopefully I saved that somewhere. How we doing? We doing all right? All right, as long as nobody complains and I get one thumbs up, we're gonna roll on. Okay, now we see an absolute value here. Remember, the absolute value, our derivative is still going to be the derivative of cosecant of 6x divided by cosecant of 6x. Do we need these absolute values? I don't think so. Let's take a look. Let's figure this out though. Okay, so y equals natural log of u, where u is the absolute value of the cosecant of 6x. Now, we have to have absolute values because, as you know, the cosecant can be positive or negative. However, the domain of the natural log is positive values only. So when we take the derivative of the absolute value of something, its derivative is the absolute value over the original, right? Like, that's so not true. My goodness. Sorry, guys. Let's just take this derivative. Let's look at cosecant of 6x. Cosecant. This is me thinking out loud. It has a derivative of minus cosecant cotangent CSC. Okay, so our derivative is derivative of the outside. The derivative of cosecant is minus cosecant cotangent. Leave the inside alone. And then multiply by the derivative of the inside, right? Because we've got some double chain rule going on here. The cosecant is inside the logarithm. The 6x is inside the cosecant. So our derivative of y really should be minus 6 cosecant of 6x cotangent of 6x. Notice I moved this 6 to the front with the negative. All divided by the cosecant of 6x. Let's give that a shot. It seems like there's some simplification possible. However, with the absolute value, we're looking at a sign change type of thing here. So where did I do that one? Here we go. Minus 6 cosecant of 6x cotangent of 6x divided by the absolute value of the cosecant of 6x. Hopefully, let's see. Well, it didn't like that at all. That's a bummer. All right, let's see what I did wrong. Today is just not a day for me to problem solve. Although she's out of the ICU, it's just not cool when your whole family's not together, you know, it makes it hard. So we're not going to stumble around. Yes. Because the absolute values go away, we will simplify this and the cosecants do cancel out as suspected. Good news. It's an easy fix. It was just, I'm not sure answer. And it's recorded for all to see forever and always. And we have our answer. Minus 6 cotangent of 6x. I'll even make this all better. And make sure it works. All right, fantastic. Now, I did skip this one. All right, but remember, you can find the derivative of x. You can find the derivative of the square root function, derivative of the inside divided by the entire inside. And it has a watch it just in case you need that. Let's look at number 10. Okay. Consider the following, and the functions over here on the left as well. If you're watching on a phone, this has really got to be pretty tiny for you. Sorry about that. But I like my monitor at home because I could actually see these side by side and have room to write. Consider the following. F of x equals 1/2 x, natural log of x to the 6th, and the point -1, 0. Find an equation of the tangent line to the graph of the function at the indicated point. Use x for the independent variable and y for the dependent variable. Okay, so as soon as I see tangent line, I know I need the derivative, and then we evaluate, and that gives my slope. Okay, so let's find the derivative. If f of x is 1/2 x, natural log of x to the 6th, normally I would simplify this x to the 6th. However, when we bring the 6 down in front, that leaves a natural log of x, and -1 is not in the domain. So I need to leave this even exponent because -1 to the 6th power is positive. So I'm not going to simplify this format right now. I'm just going to take it using, excuse me, the product rule. So we have first and we have second. So our derivative is first times the derivative of second, derivative of the inside divided by the inside. So first derivative of second plus second times the derivative of the first. So I'm going to rewrite that. Let me see, this x to the 5th and the x to the 6th leaves an x in the denominator. However, this x cancels out that x in the denominator, and I'm really just looking at 1/2 of 6. All right, let's make sure x, yep, I believe it. And then we're going to evaluate, right? So now we want to know f prime at -1 is 3 plus 1/2 the natural log of -1 to the 6th. -1 to the 6th is 1. The natural log of 1 is 0. 0 times 1/2 is 0, plus 3 makes 3. So let's give us some room here. So this is my slope, my tangent line. Y minus, and fortunately I still have it over here, y minus 0 equals 3 times x plus 1. Y equals 3x plus 3. Let's give it a shot. No y equals on the outside. Probably should make that a plus. That's not my answer. I haven't answered the graph yet, so don't believe that because that's not true. All right, maybe we'll do it at the same time. I don't want to give up an attempt. So this is a positive slope, and it has a positive x-intercept. Positive x-intercept, awesome. Positive slope at neg seems pretty reasonable, right? But this one's also positive. Is that a tangent line though? That's not a tangent line. That's not a tangent. These are the only two that are tangent. This is the only one that has a positive slope. Let's hope we have it right. All right. Yeah. All right. How are we doing? Any questions?
All good. Thank you.
All right. Awesome. Everybody else is doing good? Because I feel like I'm just cruising through this. And if I am and you're keeping up, that's awesome. I know it's hard to talk when you're probably doing your problem of the same type, huh? I get it. I know. I watch in class. I pay attention. All right. Now, the coolest thing we're ever going to use logarithms for is this right here. This is my favorite thing to do with logarithms, and really the only reason why I actually know my log properties. No, that's not true. I've taught for 20 some years. I know log properties because like probably better than my social. I use them more. Here we go. Logarithmic differentiation. Bomb. Look at this. If to find dy dx, I'm having a hard time containing my excitement. To find dy dx, we need a quotient rule, right? Big old quotient. With product rule in the numerator and the denominator. Gross. Nobody wants to do that. So here's what we're going to do instead. Check this out. Y equals x plus 1 times x minus 6 all over x minus 1. Oh yeah, my dogs are in full force right now. If somebody goes by, the wind blows wrong, I don't know, you'll probably hear them. All right, so our first step, we're going to take the natural log of both sides. And literally that comes to writing natural log in front of both sides. Oh, they love the mailman. Mailman's early today. All right, so that's it. Step 1, super easy. Step 2, simplify right side with log properties. So I'm still going to have natural log on the left, but over here, right? If we're dividing two things in a logarithm, we subtract. If we're multiplying, we add. So this will be the natural log of x plus 1 times x minus 6 minus the natural log of x minus 1 times x plus 6. All right, so quotient rule and then product rules. If I'm multiplying two things inside the logarithm, I can change that to adding the two logarithms. Since this has a minus on the outside, keep in mind that this minus sign distributes. All right, so this minus sign is going to go here. But look what we have now. All right, we can take the derivative of all these. So the derivative of natural log of y, remember x is always our variable, right? Y is a dependent variable. So the derivative is derivative of the inside times the derivative of the inside, right? The derivative of natural log of y is 1 over y dy dx. That's it. But check it out. What's the derivative of the natural log of x plus 1? The derivative of the inside over the inside. Derivative of natural log of x minus 6, derivative of the inside over the inside. The derivative of the natural log of x minus 1, derivative of the inside over the inside. Distribute that minus sign, and the derivative of the other natural log is 1 over x plus 6. The derivative of the natural log is so easy that once we use algebra to expand this ugly, horrible function, the calculus is simple. So let's find my cursor. Let's make more room here. All right, so we take the natural log of both sides, and then we take the derivatives, and then multiply both sides by y to solve for dy dx. So when we multiply by y, on the left, we'll have dy dx. On the right, we'll have 1 over x plus 1 plus 1 over x minus 6 6 minus 1 over x minus 1 minus 1 over x plus 6 times the original. And the original must have been x plus 1 times x minus 6 all over x minus 1, x plus 6. And that is the ugly answer I'm going to type in here. You could distribute, absolutely, but ooh, nobody wants to. I also, looking at the time, don't really want to type that in there. But you could trust me, right? Honest face, I'm trustworthy. Let's see. Oh, they totally simplify it. Here they have the same thing as us, only there. My 6 is going to change. It'll be different for everybody. Oh, so they like added everything together? No, we're so not going to do that. Come on now. We're not that ambitious, are we? I would rather type this. 1 divided by x plus 1 plus 1 divided by x minus 6. Sorry, I can't talk while I do this or else it's just nonsense. X plus 1, x minus 6. Oh my goodness. Still a lot to type. But I would rather type than algebra. And at this point in the semester, I feel like I know you, and I feel like you probably would rather type than algebra too. Algebra is where we make errors. Calculus, you guys got it. No problem. All right, number 12. We're going to do my problem here. Natural log of xy plus 6x equals 35. Use implicit differentiation. And we did that, right? We used implicit differentiation up here when we took the derivative of the natural log of y. So without maybe even realizing it, it was part of our process for logarithmic differentiation. Let's give it a shot. So we have, let's go with blue. So when I look at the natural log of xy plus 6x equals 35, I have a product rule inside, or I could have a little bit of algebra here to separate them. Now, we could do this problem either way. So I'm going to show you two ways. First way, second way. Now, to leave it alone and just suck it up and do it, right? This is derivative of the inside. So the derivative of x times y is first derivative of the second plus second derivative of the first all over the inside, right? Derivative of the inside divided by inside. And the derivative of 6x is 6, and the derivative of 35 is 0. No big deal, right? We want to solve for dy dx in general. So x times dy dx plus y equals -6. So I took the -6 to the other side, and I'm going to multiply by the xy at the same time. We can subtract the y. And then divide it all by 6. Not 6. How about we divide it all by x? And you can factor out that negative sign if you wanted to. This is a fine answer. I'm going to do negative 6xy plus y divided by, of course not. Let's make a fraction first. Remember, when I factor out that negative sign in front like this, we change to a plus. And that's a fine answer, and you could do it this way. But if you get in the habit of always simplifying your logarithms, it'd be nice to know that you get the same answer. So let's check it out. The derivative of the natural log of x is 1 over x. The derivative, plus sign. The derivative of the natural log of y is 1 over y dy dx. The derivative of 6x is 6, and the derivative of 35 is 0. So it looks like 1 over y dy dx equals -6 minus 1 over x. We're going to multiply both sides by y. And when we do that, what do we get? We get a -6y minus y over x. And if we combined like terms, if we tried to do fractions here, we get the exact same thing, right? Common denominator, we're going to get the same answer. So it depends on you whether leaving it is easier or simplifying it, like expanding the logarithm first is easier. I already got points for it, so I might as well mess around. Maybe -6 minus 1 over x gets multiplied by y. Mailman's on his way back. So it doesn't really matter how you enter it, because WebAssign knows, as you do, that these are equivalent and you could take either approach to it. All right, I'm going to leave the share on. We still have time. And I screwed up. I didn't make more paper for us. I could probably throw another page on at the end of this if I had to. But I think I kind of want to be done for now. I really want to be done for now. I'm going to keep sharing screen so that you guys can look through this. If you need me to scroll back up to a different problem while you're working on that, let me know. Are there any questions?
Ms. Johnson?
Yes.
I did have one question, and it's in 4.4.
Okay.
I don't know if you could go over it.
Absolutely.
Number 17.
All right, let's look at 4.4, number 17. Before I do anything, I'm going to make multiple pages here in case there are other questions coming up too. There we go. Number 17. Oh, yeah. Okay. So I'm going to hide that answer. We're going to talk through it as we look at the answer. All right, here we go. 4.4, number 17. And I'm going to copy this problem in here. So we have the answers. Isn't that handy? Let's talk through it. All right, so the velocity in feet per second is given for a particle moving along a straight line. Velocity, here's what we know about velocity, is the derivative of distance or displacement, and it has derivative of acceleration. I probably misspelled that. And I'm going to fix this. Is the derivative of distance. That's the important one. The displacement is total travel, I think. I lied. It is the integral from 1 to 14 of our function. Okay, Oh yeah, displacement is going to be the overall area. And then on this one, we'll have to break it up into parts. So the total travel, we're going to take the antiderivative. We'll have t to the third over 3 minus t squared over 2 minus 156t. And since this is a definite integral, we evaluate from 1 to 14. So we'll do 14 to the third over 3 minus 14 squared over 2 minus 156 times 14 minus, and then everything with a 1. But 1 to any power is just 1. So I'm gonna write the easy answers here. All right, so we can find this value, these values, and we're going to calculator that up, and it's going to give us an answer of, since I used that problem, minus 7267 over 6. All right, now what does this mean, right? This negative sign is what tells us that it's going to the left. Over this interval from 1 to 14, right, this particle has moved left 7,267 sixths. So quite a ways, like over 1,000 to the left. All right, so that's where it is. Now the total distance traveled, we need to look at the graph. So let's stop cheating and go to Desmos. I'm going to graph x squared minus x minus 156. And on our interval, notice how everything from 0 to 13, everything from 0 to 13 is below the axis. So we're looking at area from the x-axis down to the graph. This will all be negative. So what we're going to do is we're going to find negative this area, because when we find negative value of that, it'll make it a positive area. And then we're going to find the area above the axis just from 13 to 14, just the area here between the x-axis and the graph. So make that blue, find my pen. Total distance accounts for negative areas by examining the graph. So we'll look at the opposite of the area from 1 to 13. And add to it the positive area here from 13 to 14. And since I am recording this, it's going to be a whole lot of this evaluated twice. Let's go back here. Boop, boop. And it's exactly the same thing, only we do it twice. We evaluate from 1 to 13. We evaluate from 13 to 14. Keep in mind, we've already evaluated at 14 and we've already evaluated at 1. So when we put in our 13s, we're kind of just doing that twice. And notice how we put in 13 and down here we put in 13. So we have a negative 2197 and a negative 2197, a positive and a negative, they cancel out. A positive and a negative, they cancel out. So when you're simplifying this, there's a lot of good cancellation going on here. Actually, anyway. So you can check it out and get the values from there. Does that make sense, Leslie, why we have to cut it at 13?
Yeah, it does. Thank you.
You're welcome. And remember that ... hit pause. There's all the work for it. I was too lazy to write it. Anybody else have questions? Oh, it's a day like every other day, huh? All right. I don't mind. I don't mind at all. I haven't looked at grades. I did look at the messages on WebAssign this morning. There were a couple. I handled them. I am going to, my next step, my next thing I'm going to do for all of you is on 4.6. I'm going to take a look at the trapezoidal rule. Remember, this is going to be extra credit, total extra credit. All 5 problems will be extra credit. I'm going to work on, I don't remember. Does anybody have a preference on which of 4 or 5 that I do as an example? I'm not going to record it here now. I'm going to do it separately and then send it to you. No preference, really? That's cool. That's cool. I can handle that. I'll pick one of them, look it up, make sure it's all good. I'm going to stop recording because I'm going to keep babbling if I don't.